Hi there, I'm Hannah. I'm part of the AI software and development crew at NeuReality. Today I'm introducing you to our new software development kit, integral to the NR1 AI Inference Solution, a new end-to-end system that improves cost and energy efficiency of your AI data centers. I'm here to tackle challenges in today's traditional AI inferencing systems and sprinkle in some real demos along the way. Here's what I'll cover today. First, we'll take a quick look at the big picture, the NR1 AI Inference Solution, and how our software fits in to make it a complete end-to-end infrastructure system. Next, we'll dive into the software itself. You'll get to know the latest tools and APIs we've developed to make your projects even easier. Then we'll roll up our sleeves and look at a real code example. You'll see how simple it is to move your existing AI models, like those used for speech recognition, to NR1. Finally, I'll show you a sample of NR1 performance results, where NR1 improving your ROI and profit margins by cutting data center operational costs and saves your DevOps people time. With our easy-to-use SDK. Sound good? Let's get started. Let's start with the big picture. NeuReality's mission is to make AI inferencing, meaning the data center deployments of trained AI models and business AI applications, far more affordable. Inferring AI queries today is very costly and resource-guzzling, so much so that it keeps many businesses, governments, and entire industries out of the AI market. So to make AI sustainable economically and environmentally, we must work together to bring power consumption and costs down. The NR1 is a smart companion to any AI accelerator, whether it's a GPU, ASIC, or FPGA. Everyone is trying to deliver a better AI inference chip. But here's the thing, AI chips are only part of a much larger infrastructure. And as it turns out, it's really the CPU-centric architecture causing the underlying problems. So NeuReality doesn't compete with AI chips, rather, we complement them. As you can see here, it's a complete end-to-end AI inference solution, including a novel network addressable processing unit, or NAPU, shown on the bottom right in silver. It handles pre- and post AI data processing and offloads the CPU. Plus, we packed about 6.5 times more power on it, so it's super efficient versus CPUs. Finally, our software and APIs make NR1 easy to deploy and manage. And that's the focus of this demo, the NeuReality Software Development Kit. It puts the complete in our complete AI inference solution. So what's different about NeuReality? Let's start by understanding the main culprit of high energy power consumption and underutilized AI accelerators today. This figure shows a typical system architecture in today's AI inference servers. It includes a network inference card, or NIC for short, a multi-core central processing unit, or CPU for short, and one or more AI accelerators connected to the server over a PCIe card. That's a high-speed interface standard used to connect components on the server system's motherboard to peripherals. The blue square CPU in the middle is responsible for data movement, pre- and post-processing operations before and after the deep learning models, as well as offloading and controlling model inference, including server-side batched executions on the AI accelerators. As we took a fresh look at the ideal inference solution in the AI age, we discovered that it's really the CPU causing the biggest blockage to energy-efficient data operations and full utilization of each very expensive AI accelerator, many of which run idle due to the CPU bottleneck. That's a lot of money in silicon waste. It became NeuReality's mission to free up all that performance potential and free the flow of real-world AI data to and from data centers, direct different AI query types to the best compute engines for the job. A natural consequence of our approach was to displace the CPU and the NIC, as you can see on the top right. NR1 module contains its own NAPU. When coupled with AI accelerators, NR1 boosts their total output and achieves linear scalability. The NeuReality software can be visualized as a multi-layer stack located in the bottom left. Let's take a closer look. Looking from the bottom up on the right of our software stack, pre-trained models sit above the hardware infrastructure in the second layer, developed in deep learning frameworks like PyTorch and TensorFlow, which run in the AI accelerators. The AI software pipeline is next layer in the middle, which combine models and pre- and post-processing ops to prepare data inputs to models and compose the final outputs of the pipelines. The service layer above the pipeline includes the software for integration with orchestration and provisioning systems such as Kubernetes. Finally, at the very top lie the interfaces to development operation and machine learning operation systems to manage the full cycle of development, validation, production, and updates to each individual AI pipeline. In this way, NeuReality software takes care of all aspects of both cloud and on-premise enterprise servers to connect, compute, and scale a high volume and variety of AI pipelines in real production environments. Let's look at one NR1 AI Inference appliance on the top left, which easily installs into a server rack. This one is made up of 10 NR1M inference modules coupled with an equal number of AI accelerators. No CPUs involved. Within each of the 10 NR1M modules, there are three main components. The first is the network engine, which handles incoming requests, the blue rectangle on the top left of the diagram. The second is the top software layer, including a server application to provision AI pipelines, typical server management services like monitoring and logging, and a Kubernetes agent to manage the deployed AI pipelines and the NR1M hardware resources from a Kubernetes control plane. This is this bottom hardware layer with the AI hypervisor and multiple compute engines to accelerate pre- and post-processing operations, such as audio-video decoders, general-purpose DSP to accelerate image processing, and the general-purpose CPU primarily for scalar operations and third-party software libraries used in AI business applications, such as conversational AI used in customer service centers. As I mentioned before, the NR1M module, which looks like a PCIe card, complements each AI accelerator, boosts its overall output. In a single NR1S chassis, each NR1M can pair with 1 to 4 AI accelerators connected over the PCIe. Again, the NR1 runs with any AI accelerator, whether it's a GPU, ASIC, or FPGA. When we launched the solution in late 2023, we demonstrated different configurations with AMD, IBM, and Qualcomm, showing that versatility. As you can see on the bottom row, the hardware-driven AI hypervisor handles the distribution and management of AI jobs across all the different compute engines, the best one for the job. Both AI pipeline provisioning and K8s orchestration requests are fully handled by the software layer at the top in blue, while the AI inference requests are handled directly by the AI hypervisor. The real magic lies in the high-performance inferencing received at the AI over Fabric network engine, the top left small blue box, and directly forwarded for acceleration at the hardware level. Now, let's zoom in the inference serving path and start with an AI pipeline on the far left. Remember, a pipeline is a composition of trained AI models and pre-post processing functions. It all starts with NeuReality's graph compiler in the software development kit. It takes the AI pipeline and compiles it into a compute graph with compute nodes and control nodes. The compute nodes represent the computations of the AI pipeline, while the control nodes represent control dependencies between these computations. At the end, I will discuss the NeuReality graph compiler in more detail. For now, just know that the compute node Ds are mapped automatically onto the compute accelerator engines. The control nodes of the compute graph are, in practice, small software programs automatically generated by the graph compiler. They activate compute nodes on specific compute accelerators based on the original control dependencies inside the AI pipeline. The control programs are part of the AI hypervisor driven by tiny job processing unit components shown in dark blue square boxes. NeuReality's Software Development Kit, or SDK, spans the full lifecycle of AI pipeline development and deployment of the NR1 AI Inference Solution. The NeuReality SDK has three main parts. 1. On the left, the deployment API is used for optimizing and compiling the AI pipelines into compute graphs and generating all the artifacts, like binaries, per compute engine plus the AI hypervisor code. That's the generic term for control node programs. 2. The management API, shown in the bright pink in the middle, deploys compiled AI pipelines including the reservation of hardware resources, like compute engine accelerators, internal queues, and loading binaries onto these compute engines. Last, external AI apps and services use the serving API to create network connections to the NAAPU to send inference requests over the network. Here's a real-life business example. Let's look at automatic speech recognition, often used to improve customer service in call centers across industries like banking, insurance, and healthcare. This particular AI pipeline is built on the WAV2VEC model from Facebook. Starting on the left, it takes an audio FLAC file as input and generates the corresponding transcription text. The pipeline is based on the following reference implementation mentioned in the bottom text in white. The actual speech recognition pipeline, implemented in Python plus PyTorch, is shown moving left to right schematically as a sequence of operations. It has 4 main pre-processing operations. 1. It manipulates the input audio in exactly the same format the model expects. 2. AI operations include audio decoding and resampling, which means converting audio to mono and changing its frequency. 3rd, the model itself produces tokens with probabilities. Last, a CTC beam search decoder creates the final text from the computed tokens. With the NR1 solution, we expect optimized mapping for each of the 4 operations onto the beset compute engines for the job. First, decoding and resampling should be performed by the audio decoder hardware accelerator. Casting and padding are typical vectorized SAMD operations, which are best accelerated on a general-purpose DSP. The model is naturally mapped to the AI accelerator. And finally, the CTC decoder is a Python code from the torch.audio library that will run as is only on the general-purpose CPU. Next, let's look at the common steps for porting AI pipelines in Python on the left to compute graphs for the speech recognition pipeline on the right with the NR1 solution. First, the original AI pipeline is defined as a model ensemble, which I will demonstrate later in this webinar. The AI models can be optimized for inference using the toolchain optimizer tool, including model quantization, a technique used in AI to reduce the precision of a neural network model's weights and activations. The model ensemble is then compiled into a compute graph using the toolchain graph compiler. The compute graph is shown on the right. Rectangles are the compute nodes which implement the different ops on specific compute engines. Blue diamonds are the control nodes I mentioned earlier to activate these compute nodes on the corresponding compute engines. An AI deployment engineer, yes, a real human, can run and validate the compute graph on the development machine before actual NR1 deployment. It's done with a functional simulator, which is part of our software development kit. Once validated, the compiled AI pipeline, or compute graph on the far right, can be activated using NeuReality provisioning APIs, and its performance traced using profiling APIs. Finally, creating the client application is necessary to launch AI inferencing of the AI pipeline, whether it's for speech recognition or anything else. Thanks for sticking with me so far. You're doing great. So far, we've finished the first 2 agenda items with just a little way to go on the ASR pipeline with the toolchain API. In the remainder of our time, I'm going to walk through the steps of recharacterizing AI pipelines with the NeuReality programming model to drive ease of installation, ease of use, and ease of management. By simplifying this step, we free up the time and talent of your AI software engineers for more complex, value-add tasks. Here is a Python implementation of our speech recognition pipeline example. Pretty typical stuff with no special considerations. We captured the AI pre-processing and post-processing by separate inner classes, a best practice which also helps demonstrate porting Python to the NR1 server appliance. Here in pre-processing, I'm keeping the code high level and skipping specific functions, such as ffmpeg_decode and convert. Both implement the call function, so we can later instantiate and invoke them as functions. In post-processing, we instantiate and later invoke the CTC decoder. On the right, we have the special init and the call methods of the main speech recognition WAV2VEC pipeline. We instantiate the pre-processing and post-processing objects and the predefined WAV2VEC model from torch.audio library, showing the high-level code of the full pipeline. To port the original WAV2VEC pipeline code to NR1, we redefine it using several base classes of our SDK programming model. Base classes represent basic model types that comprise AI pipelines: Python models, OnNX models, PyTorch deep learning models, ensemble models, and others not used with Wave 2 VEC. Plus, there are like hints to the graph compiler that map out the AI pipeline operations to the different compute engines. For example, in this case of post-processing, it is defined with our nr.python model base class to hint the compiler to pack all the Python code inside the pre-processing class to be deployed and executed on the GPCPU compute engine. Let's look at a more composite example of pre-processing, captured inside the top red frame. Here, we redefine the pre-processing with two nested ensemble models using the NR1 ensemble model. One carries out the decoding and resampling. The other calls this ensemble, then performs the casting and padding ops like in the original pipeline. In our upcoming SDK production release, the ensemble model will be automatically generated from heterogeneous PyTorch models. As you can see, pre-processing functions are done via accelerated functions from the NeuReality library. This library is denoted by the NRLAB prefix. An ensemble model captures a set of invocations of other basic models and functions accelerated by NeuReality libraries. Again, it helps the compiler with generating the compute graph. With our current SDK version, it's done manually. In the next SDK versions, it will be done in a more automatic fashion. The Wave 2 VEC model is encapsulated with a PyTorch model, denoted by nn.torch.module in the yellow highlighted area on the right side. Inside, we instantiate the model and even remove weight normalization ops, as they are only relevant for training and may not be supported on target AI inference accelerators. Finally, we redefine the original pipeline on the left as an ensemble model, which integrates pre-post-processing and the Wave 2 VEC model. By itself, it's very straightforward porting. Once the original pipeline has been ported into a NeuReality ensemble model, we further compile it into a compute graph. Here you can see our graph compiler and all the phases based on the open-source machine learning compiler framework. Given the volume and variety of trained AI model types in the AI pipeline, the front-end compiler, shown in the first gray rectangle, transforms all code into a common IR. Next, the compiler optimizer applies various code optimizations and mapping operations onto the NR hetero compute acceleration engines. Finally, multiple back-end compilers generate binaries for diverse compute acceleration engines, plus compute graph description with all the control nodes for deployment. NeuReality's compiler architecture is very modular, helping you extend it with different backends for different AI accelerators from different hardware manufacturers. Next, you will compile the AI pipeline after being redefined with our SDK programming model. Here you see the compilation of every internal model in the AI pipeline, the inner ensemble models with their accelerated functions, the DL model of Wave 2 VEC, and finally the Python model. If you would like to see a live demonstration of our software team compiling compute graphs or AI pipelines, just ask. We'd be happy to run you through any part of the SDK live. We are about to wrap up on the automatic speech recognition demo on this slide. Now we can run the auto-generated, compiled compute graph to visualize the speech recognition pipeline. Here we see the different compute and control nodes. For each compute node, we see the compile time decision for its target compute engine accelerator. In our example, the control nodes are very simple. Each control node simply activates the next compute node for execution. But in general, if the AI pipeline and its compute graphs have parallelism, these control nodes will be responsible for joint operations on parallel execution paths. We use a simple Python script with our SDK APIs to run the compute graph on the NR1 behavioral simulator. On the far right, you can see that the same exact compute nodes of the compiled graph are executed simultaneously. That is, the AI hypervisor runs the compute graph, which is the fully compiled and optimized AI pipeline. Okay, that's the end of the demonstration. Before I send you off, let's quickly summarize the 5 big takeaways from the NeuReality software and toolchain API. First, we support a simple PyTorch programming model to define different AI pipelines and ease porting from Python code to NeuReality. 2. We support offloading and accelerating fully loaded AI pipelines with the best AI accelerators for the job, then using NeuReality to maximize their output, meaning no idle time. Then as you scale, no performance delays or drop-offs. Third, All our software tools have Python APIs, making it very easy to integrate compilation and simulation with standard tools and flows like ML. Ops. 4. We ensure easy validation of the AI pipelines during all stages of development and deployment. Finally, NeuReality software extends to different AI accelerators and their software stacks, making it easy for customers to install and run trained AI models and multiple business AI applications, which is the real-life scenario that AI data centers grapple with. We're here to reduce the complexity and the cost of that. Oh, I promised some proof at the beginning, so take a peek at some of our recent performance testing. Here we compare NR1S in the purple bar to two different CPU-centric GPUs from NVIDIA. In dark blue is the NVIDIA H100, and light blue is the NVIDIA L40S. Here, NeuReality is paired with Qualcomm Cloud AI 100 accelerators. We ran cost per AI query tests across 3 fully loaded AI pipelines, text, sound, and image, the building blocks of traditional and generative AI applications. And we saw very positive results. When AI accelerators were paired with NR1S versus CPU-centric, NeuReality demonstrated an average 90% cost savings. Ask us for more test results regarding energy efficiency, cost per token, linear scalability, and more, to see the difference of NR1S over CPU-centric architecture. The purple bars show NR1S with AI accelerator across natural language processing on the left, automatic speech recognition, and the impressive computer vision pipeline on the far right. The blue bars are CPU-centric first with NVIDIA H100, then NVIDIA L40S, whereas the purple bars show NeuReality NR1S paired with Qualcomm Cloud AI 100 accelerators. Let's wrap up. NeuReality set out to solve an industry-wide problem in high cost, high energy consumption, and high complexity in today's AI inferencing data centers. These inefficiencies cut into operating costs, profit margins, and also have a negative impact on the environment. To do that, we've created and commercialized a fully integrated silicon, hardware, and software solution that pairs with AI accelerators to make the entire AI data center system more efficient and tailored to AI inferencing requirements. Let's walk through the 3 main benefits to you. With NR1, you can 1. Experience affordable intelligence with up to 90% total cost savings. And more affordable AI means more businesses and governments can rapidly adopt AI to advance health and patient care, medical imaging, threat and fraud detection, public safety, customer service, and spectacular art, media, and entertainment experiences. They don't need to wait. The NR1 is here now. 2. You will experience sustainable intelligence by cutting your power consumption with up to 15x the energy efficiency. Less carbon footprint, which is some parts of the world like Europe are more highly regulated. Last but not least, NeuReality's revolutionary intelligence delivers an alternative system architecture to CPU bottlenecks and make AI easier with our ready-made software development kit. That means less complexity, time, and headache for software developers, users, and new customers like you. And because our software and hardware together are fully integrated with any AI accelerator, NeuReality boosts their output and achieves linear scalability for a fraction of today's cost. We'd love to hear about your challenges and opportunities and see if NR1S is a good fit for a pilot or proof of concept in your organization. Let's make AI easy for you too.